another DraftScience video presentation and such. Yes, we're recording. Good. Alright, so I'll play some of this, some bad physics, the same jargon, the same misdirection. I'll show how it's just misdirection, how they just contradict each other themselves. And it, goes all the way back to the physics girl video, just, glibly saying, with absolutely no apprehension, we 100% transferred the momentum, yet had a whole bunch of energy losses. It can't make any sense to anybody rational. It just can't. It's just not possible, because momentum is a real thing. It's not a fake thing. It's not some illusion. It's not telling you it's a half-truth or something, that you can have momentum in different forms of momentum or something, and that there's secret forms that you can just leak out and you never knew you had them, or you didn't account for them. I mean, it's a word. It has a value. You can't undo the value. And again, there's people arguing about units. It doesn't have anything to do with units. Okay, I mean, MV has the same structural units as 1/2 mv squared. You haven't changed the units at all. You only have m and a v. So you can't say that it doesn't have kilograms, or it doesn't have time, or it doesn't have something in it, when oh yeah, of course it does. So that's just rubbish. And I guess part of the thing that confuses things is when they do this whole Newton's apple thing. A Newton is the weight of an apple, 100 grams. So 100 grams is 1/10 of a kilogram. So here they're putting things in units where a Newton is 1/10 of that unit right off the start. Right? Right. And then you drop an apple, 1 meter, and that's a joule. Yeah. So clearly it's just not that, it can't be that complicated, and clearly MV can do it. All you have to do is change the decimal place, because you're dealing with something that's 100 grams rather than 1 kilogram. But anyway, it doesn't really, they're all just numbers for comparison in most cases. So in a lot of cases, let's not say most, in a lot of cases it doesn't matter what formula you use, because as long as you're using the same formula on both sides, it all comes out to nothing. But I thought it'd be worth just going over how ludicrous, okay, just another example of, it just can't work. And I pointed out it would be especially visible in the circumstance of navigating in space, because then the only thing that's going to matter is how much momentum hits you. It's not going to matter what size it is. Okay, big, giant, slow thing hits you, little, fast, small thing, light thing hits you. The whole idea is that there's a certain amount of energy it can impose on your spacecraft in terms of its direction. It wouldn't matter whether I eject from my spaceship a big blob moving slow or a little blob moving fast. It's momentum that's going to decide how much it turns my spaceship, and nothing else is going to decide. And so you can kind of know it from that example. But another way of looking at it, again, I'm arguing that, say if you have 1 electron, okay, and it's moving 10 velocity, or you have 2 electrons, okay, moving 5 velocity, all right, it seems kind of obvious that those are the same things, okay? That hitting something twice with half the pressure is the same as hitting it once with double the pressure. And you really can't get around that. So you could make it into a system, like understand that another piece of matter is just going to have the same electrons. Let me try to draw them the same size. And all you're really saying is I have to move this package of electrons as a package, okay? They're not going to move individually. They have to all move. So essentially, whatever energy I put into a system, I'm just saying I'm going to have to take the energy that this is going and spread it over all of these objects. And when I divide all of these objects into that velocity, what do I have at the end? And that's all you're doing. So this is 10, okay? It is. It works out that way. All right? And it's just a fact that that's all you have to interfere with this system. This is going to interfere with it, that is, cause it all to move exactly as much as this is. And I could draw it another way, is that you just think of it as terms of whatever your object is, it's just basically going to bang into a system that's bigger than it. So if you took this one thing going 10, and you banged it into things with equal mass, two of them at the same time, crash into them, and this one goes this way and this one goes this way, this one's going to be going 5 and this one's going to be going 5, and then they would do the same thing. They would hit two things, and they would go 2.5 and 2.5, and that's how you would distribute the energy over many objects. And you can just jump from here, okay, all the way to some endpoint, okay, where you're going to finally get to the actual moving velocity of the entire thing. Again, all the energy has to be spread against all of the little bits, the electrons inside of the matter. The electrons and protons are the things that have to be pushed. They all have to move together, and that means that whatever energy you put into the system is going to be spread between all of those little objects, and they're all going to have to accept the fact that you've injected energy this way, and they're going to have to move in that direction. And so there's no way to account for any of this 1/2 mv squared thing. You have to move the matter. The matter doesn't get less important because you threw one thing going faster than two things going slower. It's not going to make any difference to this. It's not going to make any difference to the factual physical thing that you're adding a certain amount of energy, the momentum, and it has to be spread across whatever the object is you just encountered. Now the fact is, in the real world, stuff bounces. Or in the video I'll play, there's a little example of a spring, and yeah, the whole spring moves, when the spring expands. Well, that's because there wasn't enough mass to collect all the energy. So because some things can't move fast enough, air resistance, this, that, and the other thing, they can't collect all the energy. And so the object ends up, bouncing around. But if you put a heavier object on, you don't have those losses. There'll be an example in another video with a crossbow versus a bow. Well, the crossbow, the problem is people don't lock the, when you're holding a bow and arrow, you're rigid. Your arm is rigid. The bow can't move because it's tied to your mass, and your mass is tied to the friction of your feet in the ground. So if you take a good stance, there's not going to be, you're destroying the equal but opposite reaction in a sense, the recoil. There is no recoil. Okay, so all the energy goes into the arrow. But if I'm using a crossbow and I'm holding it like a gun with my arms bent and I get recoil, well, I've lost part of the energy then. I mean, they're obvious solutions. You have to follow the energy, and the fact that physics just doesn't want to say those words. Follow the energy, and you'll see that there's just no room for this extra equation. It has no place. There's no reason to believe momentum gets any wrong answer. So they still haven't shown a single example where momentum is lying to you. Momentum isn't telling you the truth. There'll be no example of this. So we'll play the beginning and ending, at least, of this. It has a couple of different examples, and but it's cartoonish. Sorry to say. Very nice guy, very eccentric, does his physics thing very good, but on this subject, forget it. Not even close. Alright, so this is somewhere in the 60s.
How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business.
Yeah, well, on this subject, you did some bad business.
And on today's program, our special business is the subject of energy and momentum, two of the great immutable ideas of physics.
So again, there's just no point in calling them two different things. It's the momentum of a photon. It's a momentum of electrons. It's the momentum of all of these objects in the universe. It's always their momentum that is their energy. If they have no momentum, they have no energy. Just a fact.
And we must make clear their difference.
There's no difference. No reason to believe there's a difference. No good reason to believe momentum isn't a perfect fit for the word energy. Just perfect fit.
So, for my purpose, I go to the two cars again. You remember what we have in earlier programs? A large, massive car.
So again, the drawing looks good to start. It's got that part right. Big M,
wheels, and a smaller car, little m, on wheels. And
Now, you could point out that, well, they should have a different number of wheels because they're going to create a different amount of friction, blah, 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 blah. But we don't need that perfection for the sake of the argument. But the fact is there's going to be more pressure on the two wheels on the heavier mass, and that's going to cause a little bit more friction.
they're on the tabletop, and they're connected by a sort of elastic connection of rubber bands. Now when I pull them apart, I store some elastic energy in the stretch spring, and there is a force then which is exerted on both cars. Now what did we learn?
So again, this whole force exerted thing is just kind of, Joe, I don't know if it's very helpful to say that. The pieces of the stretched material, whether it be spring or anything else, they're going to have, you're pulling them apart and you're creating potential, by the fact that you've done that. There's all kinds of little forces in the elastic thing. Okay, so it's a bunch of little forces between electrons and protons that are going to cause the momentum of the actual spring. I mean, the rubber band, the spring, it's going to actually do something, and you've tied something to it. So it's going to have the original momentum, and you're going to drag the other two objects with that momentum. But I mean, they're not really going to have the momentum until you start dragging them and forcing them to have it.
Before, we learned that the big car has a little acceleration, and the little car a big...
Okay, so instead of using the word acceleration, we should just use the word velocity. It will have an increasing velocity. That's all. Okay, so there's a simple word. We can just get... The word acceleration doesn't mean anything. There's nothing special about anything called acceleration. Acceleration is just understanding that the velocity is changing with time. But at any one period, at any one point, the object has a velocity, and in turn it has a momentum. So it starts moving slowly, and then it reaches its whatever the maximum potential of the applied force. So if you apply the force over a long period of time, it'll keep gaining velocity. If you stop applying the force or apply a counter force, then it will stop gaining velocity. So much like when somebody jumps out of an airplane, right? They keep gaining velocity because gravity keeps hitting them until the atmosphere pushes back with 1g. Okay, that means it pushes back just as hard as your bed pushes you, when you're sleeping. So once the atmosphere collects enough energy to push back with the same pressure your bed pushes you, it's negated any gains. It's not really suppressing your velocity. It's suppressing the source of your velocity, which is it's undoing all of the force. It's equalized the amount of pressure pushing you down and the pressure pushing up, so to speak, resisting, is exactly the same amount, and so therefore you can't gain any velocity. So whatever velocity you have, you maintain, but you can't gain any more. That's all it starts taking away, is whatever you're gaining. And if you're not gaining any velocity, you can't increase the pressure with the atmosphere, so you just stay in some state. So you're not really free falling anymore. So once you get up to your maximum velocity, you're not free falling anymore, you're lying in bed. So people all talk about how the magic sensations and all this crap. Well, all that crap only lasts until you reach your terminal velocity, and then you're done having your fun new experience, because now all you are is in a wind tunnel. But anyway, don't need to be ridiculing everything that humans do, but I mean, just stupid, silly shit.
acceleration, because one and the same force acts on both cars.
So again, yes, there's one. All the rubber band cares about is getting back to its condition. So it's applying exactly the same potential to both. So unlike gravity or something else, well, that's not even a good comparison, frankly. No, I won't say unlike gravity, because in a sense, the lighter car will be able to contract quicker. Therefore, it can collect, it can move more distance, because it's going to move faster sooner. But that's it. It's just going to move faster sooner. And it's just as obvious as if I went outside and I tried to push something that's heavy, and I try to push it the same distance as something light, right? You've got to know it's going to take you a lot more energy to move the heavy thing the same distance than the light thing. well, anyway, continuing. But just understand, he's basically saying there's an equivalency in the momentum they're acquiring from the rubber band.
Now, we also saw, on another occasion, that the little car acquired the greater velocity, and the bigger car the lesser velocity, and we call the product of M and V the momentum.
Right. So he's got them inverse, just the way they should be. Okay, they've acquired the same energy from the circumstance. They can't acquire a different amount or a disproportional amount of energy. So they have the same energy, momentum. Okay, the lighter object obviously was able to move into the low pressure faster than the heavier object. That's it. And it just happens that it's exactly proportional to how heavy they are. How fast it's going to be able to move is all dependent completely on how heavy it is.
And it is not unreasonable now to say that because the accelerations are inversely as the masses, the velocities are so, and...
Well, yeah, so it's just right there. You should just be able to say, okay, acceleration is just another way of describing velocity. But it ultimately is just about velocity. And acceleration is just telling you that it keeps happening until you're done doing the accelerating part. So you haven't reached your total velocity yet, your end velocity. And you certainly can't calculate your average velocity yet.
Therefore, the momentum of the little car is equal to the momentum of the big car. So their momenta are equal. But now what?
Right, and so there's nothing else to talk about, right? You're done. There's no other thing to talk about. Their momentums are equal. If I hit a spaceship with the slower, heavier car, it will impart just as much directional change as if I hit it with the faster, lighter car. Both have the same potential to move matter. Both of them have the same potential to do work. One doesn't have more potential. More done doesn't have more joules. And by their silly equation, the light car now has more energy. Somehow it acquired more energy out of the event than the heavy car by some magical living force, magical wooey bullshit. I mean, again, it's all just such a religion.
Watch.
They might as well be telling me about the Holy Ghost energy. It has just there's absolutely no reason to think you're not already done. You've described the circumstance rather completely. The lighter car is easier to push, therefore the same force pushed it further in the same amount of time. Not a surprise at all. It doesn't mean it contains more force.
Watch. Is it not true that the smaller car went the greater distance? That is, if I let them come from a place of rest and meet, they would meet somewhere in here. This is the distance the big car would go.
Right, and we know this doesn't mean anything, right? Because we know that, if we do the double the velocity thing in gravity and we measure distances and it goes 4 times the distance to double the velocity, we know that this fake relationship exists, but we know that when they land, they will have the same momentum. So we know that we can change the weights and we can make something go further. But going further has nothing to do with having more energy. So again, because they have defined work as how far you go, and again, it's so easy to unravel that as nonsense, because to push something heavy takes a tremendous amount more work. So if we make them go the same distance, the light thing and the heavy thing, I'm going to push them exactly the same distance. It takes a lot more energy to push the heavy thing than the light thing. That you're going to do a lot more work to get the same distance.
And this is the distance the little car would go. So the little car goes the greater distance. S, little s. And now I define...
So that makes sense somewhere, I guess. S is distance. Well, whatever. It's not very good vocabulary.
For you, what is meant by work or energy in physics? The product of a force and a distance.
So there you go. The product of a force and a distance. So it just couldn't have anything less to do with the truth, right? The truth is distance doesn't tell you anything about, especially in circumstances where the distance isn't going to show you how much energy the object has. Okay, how fast it's going is only one piece of the equation. The mass is an equal piece of the equation, and you have to consider the mass. You can't just consider the distance. It doesn't make any sense to do what they're doing here. It's idiotic to say work is distance, because it's not. I mean, in simple experiments, it's proven not to be the same. I mean, lifting 100 pounds 1 foot is a lot different than lifting 1 pound 1 foot. There's no way you can say, it's the same amount of work, same amount of force. Of course not.
The product of a force and a distance. So, the same force acts on both cars, but for the big car, the distance is a little one, and for the little car, the distance is a big one.
So again, you can't make it make less sense to say, well, quite obviously, but that doesn't mean there's more force. Clearly, the force is made out of the mass and the velocity, so there's just no point in having any other conversation. Now, when Newton said F equals ma, he's using acceleration because he's talking about the acceleration provided by gravity. It's a gravitational statement. If you really want to talk about the real world, all you care about is the end velocity. All you care about is what's the velocity you imposed, period. And that's the momentum. Force equals mass times velocity.
And these products are not equal. So we learned this astonishing thing, that although the forces are the same, the accelerations are inversely as the masses, the distances are inversely as the masses, the momenta are equal, but the energies are not.
Okay, so it just makes no sense. Like I said, if he takes those two sources of energy and puts them in outer space, like I said, there's no physics that makes it any sense to say to you that if I try to steer my spaceship with those numbers, that somehow the faster object capturing the faster object, the lighter, faster object capturing it, okay, will move my spaceship more. There's no logic, there's no physics, there's no experiment, there's no anything that justifies this. Again, if I put a generator on those carts and I try to generate electricity from their motion, I'm going to generate the same amount of energy from the heavy cart as I'm going to generate from the light cart. The torque on the heavy one will way overcome the distance difference. So yes, the lighter car moved a greater distance, but it moved a greater distance with a lot less torque. So if I put a generator on the wheel, I'm going to slow that light car down really fast, and I'm going to have a lot harder time slowing down the big cart, the heavy cart. And so in the end, I'm going to turn the generator exactly the same number of turns.
Very important idea. Now this business...
So it's a really critical error. Like I said, this is as big as getting plus and minus wrong. Now that was an honest mistake. This mistake is right in their face, a nonsense. It has a terrible history. It's just really bad physics. The very notion that you can conserve momentum and lose energy, it's such a silly notion that somehow I can diminish the speed of an electron, with some friction. I can do work somewhere in the universe with my energy and then somehow transfer it all anyway. Somehow I don't lose any. You can't possibly create noise or sound or heat or any of that stuff. It has to come out of your momentum. It has to. You can't transfer your momentum and do work besides. Impossible. It's so impossible, it's stupid. I mean, it's just stupid to make this argument.
Of energy, beautifully demonstrated as follows. Look what we have here. Here is a curved track, straight and short here, straight and long here. Now this end of the track is at the very same elevation above the tabletop.
Right, so, you can sort of tell this is just going to be a pendulum. It's just a funny shape. And the fact is, at the bottom, the object has exactly the same momentum. It has its peak velocity right there, and on both trips, it's got exactly the same momentum going in the opposite direction. So it's completely equal, and his argument is more distance somehow have more energy on the longer end. That somehow there's more energy involved. There's no more energy. There's exactly what you put in. And it's just that you're lifting the ball against gravity slower. That's all. I mean, more incrementally. That's it. So the ball goes faster. Same difference. It's the same momentum. You can't change the momentum.
Up as this end. I have shimmed it up on that end to get it horizontal. And what do? We put a ball at the top of this track at this end. It has so much potential in it.
Shouldn't have said faster. How far it goes is different. But its velocity, its real velocity can't change.
Energy being so high above the zero potential plane, and I let it go. Now it is losing some of its potential energy, gaining kinetic, losing energy really because friction is in the system, and we hear sound, which costs the ball.
Right, so that's just a tiny percentage of the overall energy, and that can be seen by the fact that it keeps going. So we can talk about all the ways it's losing a little bit of the momentum. Yes, okay, but they have nothing to do with changing momentum into some other form of energy, or any notion that if I was to, take the energy created on one side of the track and take the energy created or the work done on the other side of the track, that I did more work on one side than I did on the other side. They have the same working potential. It isn't more work to lift the ball on the longer track.
Something, it cannot produce the acoustic energy for nothing. Now what do some think?
All you're doing is changing the rate at which the velocity is reversed. I mean, obviously the momentum changes through the whole process. It's losing momentum in one direction, and then it's going to, getting it all back in the opposite direction. So it's going to return to the center with essentially the same momentum it went up with. And all you're saying is through this path, I'm changing the momentum slower than this path does. That's it. But there's no work. There's no extra work done.
That coming down this long track, the ball down here will have enough velocity, enough kinetic energy of motion to put it up over the track here. But that is not so. If the system were absolutely ideal, no friction at all, which is impossible, the best the ball could ever do would be to go to the same height here.
Right, so that sort of so right there he's debunking his own theory. The greater distance has nothing to do with it. Okay, I can't make energy by having things go slower or faster or any of this nonsense. I can only make more energy by how much mass and how much velocity. That's all I need, is those two components, is mass and moving a velocity. Obviously, like I said, this experiment is complicated because you're basically converting momentum. You're changing momentum in one direction into gravitational potential, and then allowing that potential to recreate your momentum. So it would be a nicer example if you were pushing it into some sort of more easily to understood pressure, like a spring or something you could just watch what it's really doing, which is just taking the energy, putting it into some storage device, and then you're just letting the storage device release the energy. But technically gravity sort of works that way, but clearly you're not storing it. When you go against gravity, you haven't stored any real energy any place in the universe.
And since we are in the real world and friction plays a large role, the ball can never go as high on that end as I let it go from on this end. Watch it. Oh, it did. I'm glad it...
Yeah, whatever. So who knows how fake this is, right? Like, I'm glad it did, because then I can tell you another story.
Did, because I said it wouldn't. So somebody says, Professor, the experiment failed. No, I think what I have done, I manipulated this end a little improperly so that this end is higher, and therefore it did what it did. So you see, a lesson to be learned. Experiments never fail. I'm going to lower this a little.
Well, except for the part where they fail. But anyway, yeah. So we know this story, but I'm just saying, it's clearly there's no extra energy. No one could rationally argue that one side is the ball is moving exactly the same velocity in opposite directions. It's exactly the same mass, obviously. It has the same momentum. No rational person could argue it's doing more work on one side than it's doing on the other side. I mean, it's just not a rational argument.
And now I hope that this end is the same height as that. Now watch it. Oh, that's it. And less, and less, and less, and less, and less, and so on until the energy of the system is spent in friction and in producing sound and in vibration. A very...
Right. So, but the momentum was always at the bottom. It had exactly the same momentum. And at the top, you could argue it had the same momentum, which is zero, because it wasn't moving. Okay. So it has maximum velocity at the bottom. And it has maximum amount of energy. And it really doesn't matter how you play the lifting game. It's the same energy work, you know. You've lifted it the same distance over the same time, so it really just doesn't matter whether you traveled more distance.
beautiful demonstration, a device which I call my energy track. Now,
so why he calls it the energy track, who knows, right? He didn't tell us overtly anything like what I just said. He didn't say, well, the momentums are obviously the same. It's obviously the same amount of energy. Now, I guess he's implying that one side is more work, but he didn't state it, right? He didn't say, look, it's traveling more distance. It must be more energy. Going this way is more energy than going that way. He didn't say that.
Consider this business of energy further. Here is a block of wood. Here is a nail. I drive the nail into the block of wood. Oh, says somebody.
Okay, so this all has just about nothing to do with the conversation, except that, you know, we all know that, that these transfers can be inefficient or efficient. So when you're transferring the energy, you can, transfer it in different ways. So if he was pounding into a spring, the efficiency would be much higher than pounding into a piece of wood. So obviously when he's pushing the nail in, he's also pushing the wood out and doing a lot of other things. So if you were to measure the energy based on how far the nail went, that's not telling you even half the story, right? Because more than half the story of the energy, the momentum, is going to be in doing things besides putting the nail into the wood. That the depth of the nail is maybe it's only 40% of the actual energy you put in terms of all the other things you were doing to the wood. You lost the motion of the momentum in a lot of different directions besides the nail going into the wood, is the point.
What kind of physics is that? Astonishing physics. Why? I am doing work on the nail. The nail is doing work on the wood to separate its particles. And when work is done, when it is done against friction forces, heat energy always arises. Heat is a necessary consequence of work done against friction.
Right. Work done against friction, which, it's kind of a tricky word. Work done against interaction, because that's what friction has to involve. It's an interaction. So there are interactions that are efficient, and then there are interactions that aren't efficient, where that scatter your energy, you could argue. So, but it's always going somewhere, and the only stuff going somewhere is your momentum. You don't have any other stuff. You have momentum, you have an electron moving. That's what it's all made out of. You can't say because it's moving a certain way or doing a certain... No, it's just about the fact that it's a thing of definite mass moving a definite speed. And that's all it has, is its momentum. There's no energy outside of momentum.
It's proof. I'm going to pull that out. Oh, what do I feel? Too hot to handle. Accordingly, the work I did on the nail has been commuted to friction. Now,
part of it. So again, it's just... All right. But obviously you can't conserve momentum if you're creating those kinds of effects. If I couple two trains together and I transfer all the momentum, that is, I take a one mass object with a 2v and I bang it into another object, and so now I have two m's and one v. I mean a half a v, half the velocity. I can't conserve the momentum and then argue, but I have a whole bunch of losses to the environment. It's impossible. The losses have to come out of your momentum, just like the idea of the car going around a turn or something. The turning friction, the extra adhesion required to do the turning has to take away your velocity. It has to feed on it. It has to use your velocity to get the energy to make the turn.
There are several kinds of energy. Several kinds which we need to consider. Mechanical energy. Mechanical energy.
So again, it's all one thing, energy. There's no point in having these categories. It's all movement of mass. It all comes down to movement of mass. Electrons and protons are the mass. They have to be moved. That's all it ever is.
Thermal energy. I just showed you that with the nail heated by
So obviously the thermal energy is you've created more velocity in the electrons and protons. You've increased their momentum. That's all it is. You just haven't increased it in the same direction you were going.
It in. While we're talking about thermal energy, here is some popcorn. Some popcorn. Now you know that if you apply thermal energy to the popcorn, it soon, as a result of this application of thermal energy, of heat, explodes. Why? Because we gave energy to the little bit of water in the droplet, in the kernel of corn. It expanded enormously. How many times does it expand? Fantastic. 1,700 times. Isn't that fantastic? No one.
No, it didn't blow up any popcorn.
The kernel explodes with a rupturing force. Mechanical energy, thermal energy, acoustic energy. Sure, my vocal cord.
Yeah, so you're moving a bunch of molecular atoms. I mean, at least you're changing the shape of atoms, let's argue. Changing their shape means you have to move electrons and protons again. But that's it. There's just the momentum.
Are in vibration, and that's the only reason you can hear me. I am giving rise to excitation of the air in this place, and it is falling on your eardrum and putting your eardrum into motion.
And the trick is that it does it very efficiently. So sound moves without any friction. So it just keeps moving.
And the bones in the ear, and finally the impulse gets to your brain. Acoustic, magnetic energy, electrostatic energy. Electrostatic. Let me show you that, because it is absolutely exciting. Watch this. Watch. I have here some cork dust, which I put out on the table. Cork dust. It is lifeless and dead and inert. Here is a Bakelite hard rubber rod. Now the rod, I say, and later we will say more about it on a program on electrostatics, the rod is electrostatically neutral. I bring it near the cork dust, and what do I see happen?
Nothing.
Answer, nothing. Seeing nothing happens is a very important thing to see.
All right, so this is a little bit off the subject, frankly. How much the work in terms of removing electrons from a surface. The inefficiency of the transfer of the momentum is probably rather extreme. And and then he moves on to just dropping a weight on a nail again.
Doing some mechanical work on it. I am endowing it with potential energy. Here is a nail in a block of wood.
So again, you didn't really endow it with anything. It doesn't have any of this thing called potential energy. We just know that gravity means something. So because you can now move in gravity this great distance, so you're going to be in the gravity for quite a while before you're stopped, and therefore it can't collect any more gravity. The bucket will collect a certain amount of gravity in the time it takes for it to fall, and in that time it'll collect your momentum. It'll collect momentum from gravity. Gravity will fall into the matter bucket, okay, the mass bucket. And so the more mass you have, the bigger the bucket is. You collect more gravity. So in the time it takes for it to fall, it's going to collect gravity. And in that time, it's going to gain momentum.
And I release the weight. Look what has happened. It has driven the nail into the block. The heat developed here, very substantial.
Wow, big surprise, huh? Yes.
A toy. Energy. A toy. A spring. If I do work on the spring, I store energy in the spring. There is a so-called suction cup on the bottom, and in another program I will show you that word suction is not a good one ever to use. But
yeah, it's called a vacuum cup or something.
I'm going to put a ball in this upper platform, push down the spring, storing some energy in the compressed spring. Now the energy is available to do work for me on the ball. When the atmospheric pressure seeps into that so-called suction cup, it will let the spring loose, and you know the consequence. Up will go the ball. There it goes. Up went the ball. And there was something else. There was some action taking place in this projectile mechanism, which bears also on momentum and energy.
Yes, but he won't go into that. But obviously that's the recoil part. And you won't have the recoil if you put a heavy enough object on the spring. Then it will be able to, it'll have enough time to impose all of its energy into the object instead of leaving some of its energy still available and therefore pulling the whole device up.
Consider this business of momentum. This gun is a toy, and so we need have no fear about it, but don't play with guns. Concerning momentum, if I shoot the gun holding it far from my shoulder, will it not kick very severely and hurt me? Why? The mass of the gun recoils with a certain velocity, the m and the v, constituting a certain momentum. How do you avoid this kick?
Yeah. So he's. This isn't a very good description either. The whole point is to make the one side of the explosion into as heavy a wall as possible, because the heavier that wall is, that the gun is, the other side of the gun's explosion is going in the other direction, right? I mean, it's pushing the bullet this way. It's making an explosion. The explosion is putting pressure on both sides. So the trick is to make one side so massive that all of the energy has to go the other way. It has to reflect off the massive object. So you want to try to force the energy to reflect off your heavy mass and go into the bullet instead.
Hold the gun tightly against your shoulder so that...
I mean, obviously some of the reflection can never catch up to the bullet, but once the bullet starts moving, the pressure can't, reflected pressure would be behind, and it might not be able to add much more velocity to the bullet. But clearly, you want that's the preferable direction.
When the gun recoils, you and the gun constitute a larger mass and therefore less recoil velocity.
So it's not about your velocity, okay? Technically, it's about the fact that you are actually recoiling. So the point is you're preventing the recoil. You're stopping it from happening.
An excellent demonstration of momentum conservation. Consider a toy made for 3-year-olds. Here is a little toy, a teddy bear mounted on an elastic shaft through his shoulders. He stands in a vertical plane because his center of gravity is below his axis of support. And now what am I going to do? I rolled him away, and he rolls back.
Yeah, not very interesting.
Such a toy. An array of geared wheels and a shaft.
Make sparks.
I am showing the transmutation of mechanical work into thermal energy as well as into light, because when bodies get hot enough, they become incandescent.
Right, and all of it has to come out of the momentum you put in. There's no kinetic energy. There's no special kinetic energy. I can't make the thing lighter. I can't do some trick to make more energy. I can't make more electron activity merely by saying I'm going to use lighter things. It doesn't work that way. Lighter, faster things. It just can't work that way.
Energy, momentum, very important. Now, as one views the history of this subject, I invite you to study it yourself, because for 150 years there were...
Now, this is the bizarre part, frankly. It's pretty bizarre. So that's, almost the whole video is just for this.
Was much dispute on...
All right, so he's conceding that for 100 years or more, there was an argument about this thing called energy. And the context of the argument is essentially the MV thing, that's Newton. Okay, before him, it's Descartes or whoever. So it's this really fundamental just notion that this is what makes the universe go round, is the fact that things have mass and velocity. And the mass and the velocity causes things with mass and velocity, things with mass to change their velocity. So we're constantly giving and taking away velocity from things, okay, based on our mass. The more mass you have, the more capacity you have to interact, because you have more little bits to interact with the universe.
The difference between MV and MV square.
So this is the funny part, right? I mean, he doesn't even put the half in front of it. So you can just see that these are hugely different numbers you would get, right? I mean, squaring the velocity, this would be a gigantic number compared to this number. I mean, just exponentially bigger, like 4 times bigger. Well, it's whatever, somewhere between 2 and 4 times bigger numbers you're going to get depending on what the mass number is. But squaring the velocity is just a gigantic difference in the amount of energy you could say you were deriving from something. They're two insanely different amounts, and they're basically claiming to be describing the same thing, and the physics took no side. So like wave-particle duality, they have a real energy duality, and they left it there, even though it can't. One of them has to be right and one of them has to be wrong. There's no, they both make sense. No, it doesn't make any sense to keep both of them.
Which was settled by a Frenchman named D'Alembert.
So it really wasn't. So so I haven't even found him in my research of the history. I haven't heard that Alembert name. There was some Bernoulli name, and there was a few other names, but yeah, that one wasn't in there. So again, this is Leibniz's idea. It was called the living force, and it was resolved mostly by propaganda in France. Who was popular in France get to decide the question, and apparently the rest of the world just followed along for some reason for which I can't understand, except the fact that a lot of big names were for this nonsense. And they're the same names you hear when it comes to the whole wave-particle duality. So we're gonna hear one of the names. Okay, so we have the Young, and again, it goes to the Young double-slit experiment. Yeah, well, the Young guy is exactly one of the guys who put the half in front of it and called it kinetic energy.
But who gave rise to the problem in the first place? A young Dutchman by the name of Christian Huygens. And I want to show you a picture of him as a little boy.
So again, this is not Huygens. Huygens did not start this controversy. Leibniz did. That's clear. So Huygens was certainly on their side because he was a wooist, but he didn't start it.
The age of 11, an enchanting little rascal. And I shall have more to say about him sometime on a program.
Some stuff is a little bit just too weird. Enchanting little rascal. This is just scary.
On light, because he spent his youthful days throwing pebbles into the canals in his native Holland and watching the ever-growing circles of disturbance, and thus was led to the idea of the wave motion of light.
Right, the ether notion of reality. And that's the irony. Is conventional physics is really just ether physics. It's, they won't say it, but that's all they are.
And here, finally, is a picture of him in his later days with his what shall we call it, wig.
So he barely made a contribution to this argument, as far as I can see. He didn't write a whole bunch of papers on it or any of that kind of stuff. So yes, he's connected in the sense he was certainly on the camp of the silly definition of energy, but it's not really there in the history.
Now, the idea of momentum must be clearly distinguished from the idea of energy.
So, and how do you distinguish it? It's impossible to distinguish it. So if you make any energy, you have to take away something's momentum. So again, if I'm going to transfer energy to another system, and I'm going to make, I'm going to take, the same amount of momentum, and I'm going to put it in something else. It is not possible that I made any sound. It's not possible that I heated anything. It's not possible I made any sparks. It's not possible I did any other work in the universe. If I'm stimulating a whole bunch of other atoms in the universe, then I cannot possibly transfer 100% of the momentum. It's never happened. It'll never happen in an experiment ever. It'll never be demonstrated as being possible. You'll never have them actually do one of these experiments where they conserve 100% of their momentum and lose 250 joules of energy. They'll never show you that happening in any real world experiment ever, because it's just theoretical garbage.
And I thank you for your attention.
So you saw it. I mean, he didn't even put the half in front of it. I mean, shit. All right. Yeah, this video's getting long. All right, so there's this another one. I'm just trying to find the experiment. That's what I'm trying to find. I'm finding all this other funny stuff in between. So this is some evil motherfucking hunter creep. Okay, so he keeps putting his hunting stuff in here. About how fast you can shoot your arrow into the poor little creature. If you maximize your capacity to make Bambi an orphan. I mean, ew. Creepy motherfucker. I mean, these people that celebrate going out and fucking an animal's day, just saying, I'm going to fuck over an animal for fun today. I mean, nature sucks, but we don't have to. I'm just going to throw that much philosophy in here, but fuck this guy. I mean, I just hope he gets what he deserves. I hope he gets what he gives. I hope he gets, choking on an arrow in his throat.
Is directly proportional how much damage it will inflict when it strikes something.
Okay, so
the stone will do more damage for the given momentum. It is the square of the velocity in the kinetic energy equation that makes this possible.
Why isn't it working?
Let's do some math to show what we just...
I'm just going to have to reload it. I mean, that's just... I can't stop it. It's not starting. It's... what a mess. Anyway. All right, so he goes through all the words, momentum, this, that, with acceleration, velocity, mass, blah, 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 blah. And some of the definitions are fine, but they're all just a little bit loose and whatever. But this whole idea, he overtly makes this argument. Somehow I just keep making things lighter, and I'm going to make them more energetic. I'm going to give them more energy.
It's more kinetic energy than the rock weighing 10 kilograms.
So he says so he does this size thing, which is you don't need to do because we know we can have 10 times the mass in the same size package. So obviously it would make sense to make the bullets the same size and just give them a different mass and say, okay, they have a different mass and different velocities. But can I really say if I was to move a spaceship with their energy, would I be able to move it more with the smaller object? And the answer is clearly no. It doesn't have the torque, you could argue. You can understand that the mass is sort of like torque. It's about the, how enduring is your pushing force. How much durability does it have? I mean, do I just hit it once and it stops, or do I have to hit it 4 or 5 times before I can stop it? I don't know what comparisons to make. I mean, if bears came in this variety, fast, light bear versus slow, heavy bear, do you really think there's going to be some kind of huge difference about, how you're going to fight off the bear, how much work it's going to take? Come on. I mean, little, lightweight punch versus a big, heavy punch. It's the same energy. Come on.
Given momentum. Kinetic energy is directly proportional how much damage it will inflict when it strikes something.
So this is this word damage again. So it's not going to be damage based on actual movement of actual molecular material. So he doesn't, we're not going to be doing any experiments here where we actually collect all of the energy the object imparted into the other object. So none of this is done with any clinical comparison to any real world experiment. Like I said, no spring experiment, no experiment showing where you collect this great deal of extra energy, where you show that it has twice as much energy, that you store it in a Duracell battery, you get it off of a generator winding, you turn a windmill, you turn a water wheel, you do anything with this extra energy. It'll never show itself because it doesn't exist.
The stone will do more damage for the given momentum. It is the square of the velocity in the kinetic energy equation that makes this possible.
Yes, well, it's not possible, and it's silly, and it's stupid, and you should kind of know better. Just know that it's obviously not 100 times more damage and all of this kind of crap. It's obviously not.
Let's do some math to show what we just talked about.
Yeah, I don't know if this is worth it, just because he doesn't do any math with any kind of round numbers, and so you really can't follow any of it.
The stone is moving at 40.25 meters per second, or about 90 miles per hour. Plugging the stone's information into the kinetic energy formula, we see that it has a kinetic energy of 81 joules and a momentum of 4.25 kilogram meters per second.
Right, and you could just make that 40 instead. And say it's 40 joules.
Since the rock has the same momentum as the stone, you can calculate its velocity by using this weight momentum. Velocity equals 0.4025 meters per second. Now that we have the velocity of the rock, we can calculate its kinetic energy, which comes out.
Yeah, I wish you would have just told me how fast it's going in miles per hour like you did. You said the other thing's going 90 miles an hour. How fast was this thing going? Who the hell knows? So anyway, it's pretty hard to make anything out of this. So obviously the other number he got was whatever it was, 70 or something, and so this is only 0.81.
To 0.81 joules. The momentum of an object is proportional to the object's velocity.
So it's obviously proportional to its mass just as much. It's just that doesn't mean anything. Momentum is clearly proportional to mass and velocity combined as a unit. You have to lower the mass or increase the velocity. But there's no proportion to just the velocity.
Readily applies to crossbows and rifles. When the arrow leaves the crossbow, it has the same momentum as the crossbow, which recoils, due to the preservation of momentum. The arrow has much more kinetic energy than the crossbow, Looking at this more deeply, much more of the crossbow's stored energy is being transferred to the arrow than to the crossbow, as kinetic energy and momentum.
So again, this argument fails just because all you have to do is secure your crossbow. That is, securely mount the bow to your body and not allow it to move. So if the crossbow is well secured, then the energy goes into the arrow, and all of this is horseshit then. And again, the crossbow is going to have a higher velocity and be a lighter arrow, so clearly it would be more effective, blah, 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 by his definition. I would argue that no, the momentum is going to be decided by exactly the velocity and the mass, and the proportions of how much torque you put in, or how much pressure you put into the bow itself. How many pounds of pressure you're able to put into the much smaller crossbow.
The arrow has a greater velocity than the crossbow. Let's try to put this into real-world terms. To use units that we're familiar with, grains and feet per second, there has to be a conversion of some type.
Oh, shit, fuck it. The music, I just forgot that this had this cruddy music in it.
The conversion results in new formulas and units. Kinetic energy is now 1/2 times grains times feet per second times feet per second.
Yeah, well, let's just forget about all that. Let's see what this is going to be. What kind of argument? Well, it doesn't really matter. His argument is he's just completely falling for the bullshit. And there's just no point. Again, it doesn't matter how much the rifle weighs if you've connected it to your body. The weight of the rifle becomes irrelevant because now it's the weight of the rifle and your body. That's what has to recoil, the much larger mass. And then if you put your body against a brick wall, now you weigh even more. Now the gun weighs a ton. Okay, and the gun's not going anywhere, and the energy will have to go into the projectile or into the air. Again, if projectiles leave faster than the pressure can be imposed on them, then only part of the pressure can ever get to them. So if they're light enough, you obviously can't shoot them with all of the potential energy because they've already left too fast for the rest of the spring, say, to work on them. Because the spring has a certain limited speed at which it can release the energy. It can only release it so fast. And if you go faster than the spring can release the energy, obviously the spring can't give you the energy. All right. So yeah, that's probably enough for today. There's just a ton of this kind of crap. So maybe somewhere in all of this crap we'll have somebody actually do the experiments to capture energy. To actually show when you capture the energy with a nice, good clinical experiment, you'll find that momentum is always reliable in telling you the energy, and the kinetic energy formula is a lie because you can never, ever, 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 ever use the extra energy it says exists. You'll never be able to ever use it to do a single shred of work in the universe. You will never accomplish any work in the universe with the kinetic energy formula results. All the energy it says exists, you'll never be the energy beyond the energy of momentum. You'll never realize any of it in any experiment ever. All right. Yeah, that's enough for this video. Then we'll take on comments and whatnot in another video. I mean, the comments are just keep doing the same thing. You don't know Newton's second law. You don't know Newton's second law. You don't know Newton. I mean, obviously this isn't Newton's equation, so to pretend it's some derivative of Newton's equation is just nonsense. You're just playing a game. Well, because I used the acceleration formula, I can now double the velocity. I can square the velocity because I'm going to consider acceleration times acceleration times acceleration times acceleration. Because I'm going to say how much velocity does it have in a unit of time, and then I'm going to add another unit of time and another unit of time, and I'm going to call that the same thing as squaring. I mean, it's silly. It's not a rational derivative, and it's certainly not part of the controversy in the sense that the clear argument was between momentum being a definition of energy, which none of you will ever show any evidence where momentum is wrong. You'll never show us where it didn't have enough momentum to do the work that got accomplished. You'll never show the experiment where momentum gets the wrong answer. You'll never show it. And yet you're going to say it's the wrong answer. It's pretty amazing. All right, anyway. So, yeah, I mean, I've done my job. You people are just belligerently religious. That's all. You're just fundamentalists. You're just going to believe in your Holy Ghost. It just doesn't matter what anybody says. It doesn't matter how much evidence they can show you. It doesn't matter how much logic they apply to your nonsensical beliefs. You're just belligerently loser, stupid retards, and you're just going to die that way. Defending a bad idea. Jumping on board a silly bandwagon. Glorifying crap. Just, disgusting and such. Alright, so anyway, get the hell out of here. Alright, this has been a DraftScience video presentation. Gave me a headache.